Okay, welcome to the second part of 6.2 rational functions. Rational functions are a really hard topic to uh, fight. So if you actually to like conquer. So if you need any questions, ask me down below. So this is the final thing that's actually in the book, but I want to do extra because I want to prepare you for pre-calculus, and if you are doing advanced, prepare you for calculus. So I have to do the extra 4 slides after that. So 6.2b, complex rational functions. How do you transform a linear rational function? So this is a linear rational function where what I call it a linear rational function is probably not linear, but where x, like the x's are both degree 1. So that's the linear rational function. It can be directly observed as a translation. First of all, you actually do the synthetic division. You do the synthetic division, right? And then once you finish the synthetic division, you'll get this, and then you'll do this, and then after that, you can write the statement. The graph is a translation of 3 up and 2 to the right, because x minus 2 is the left and right, and the plus 3 at the end of every function, that's the up and down. So let's do some practice. 3x minus 5 over x plus 1. So let's do the synthetic division. It's x plus 1, so the root of x plus 1 is -1. Gotta put -1 down there. Okay, put the 3 down. -3, -5, -8. So then we have 3 minus 8 over, and then the whole thing's x plus 1. So we can say this is a translation, this is a reflection, because it's negative, right? So -8 over x plus 1 plus 3. So reflection on the y-axis, a reflection of the y-axis, 1 to the left and 3 up of 8 over x. And it's also like vertically stretched 8 times, but that's not that important in this case. So as you can see, this equation right here, we have everything has a common kind of a common denominator, like a common factor of 2. So we could just do -2. We can pull -2 out of here. Actually, the negative isn't even necessary. So we'll just do 2 -7x plus 6, no, plus 3 over 2 times x plus 2. And then we could just erase that, and then you'll get this is the same function. This is the same function, exact same function. So then we can do this now. Now we can do the synthetic division. X plus 2, -2, and then we do -7 here and 3. -7, put it down, and we have 14, and then 14 plus 3 is 17. 17, so now we have -7 plus 17 over x plus 2. 17 over x plus 2. So we can rearrange that to 17 over x plus 2 minus 7. So it's a translation of 17 over x. 7 down and 2 to the left. That's simple. Okay, now if you're in, oh god, yeah, this is a mess. Give me a minute. Okay, I've already done everything. Okay, so rational functions with degree higher than 1. So if you're doing regular maths, or if you just don't want to be bothered with the rest of math, the rest of the math, like the harder math, then just you can leave the video now. But this stuff is really cool to learn, especially when you get it. So we have rational functions with degree higher than 1. So our for example, this rational function has the bottom has a degree of 2. So there's 6 steps to um, 6 steps to conquering this polynomial, uh, this rational function. You gotta find the vertical asymptote, the horizontal asymptote, or slant asymptote if you have any of them. You gotta get an x-intercept, a y-intercept. You gotta test for symmetry, and then once you've done all that, pick some points to get the general shape of the graph. For example, I got the y-intercept, I got the x-intercept. It's 6 over 5 and -6 is 6 over 5. Where is it? There. And negative 6 right there, right? And then I got the vertical asymptotes, which is you fact the bottom. Whenever the bottom is 0, there's no solution. So the vertical asymptotes is just when it's 0, which is 5 and 1. The horizontal asymptote, we have this kind of rule set right here. If the top degree is smaller than the bottom degree, the asymptote is instantly 0. If the top degree is equal to the bottom degree, so for example, if this was x squared, you would take the coefficients of both of the the leading degrees, and then you would divide them, and that's your asymptote. So for example, if it's 2x squared over 4x squared, that will be 1/2. So that's your horizontal asymptote. If the top is bigger than the bottom, then it's a slant asymptote, not horizontal asymptote. And I'll tell you what a slant asymptote and how to do that later. It's quite confusing. So the slant asymptotes, you do the actually I'll tell you right now if you understand this, but I'll give you an example. You do the long division of the numerator polynomial and the denominator polynomial. You set x to infinity, set x as approaching to infinity, and if any part of the equation becomes 0, you discard it. So you probably didn't get that, so the example is next slide. I'll test all the points. I did all of this, and then this is the graph that I got, and this looks pretty okay. It looks pretty a good graph. Okay, this is our slant asymptote example. So f of x, so you could see the degree is higher on the top than on the bottom, so we have to do all of this, right? This is our vertical asymptote, 0 and 1. I didn't do the whole step, but we're gonna do the whole step for the next one. There's no horizontal asymptote, h equals none, right? The slant, I did this whole long division thing, and I got x plus 1 plus x minus 2, x minus 1 over x squared minus x. So this is kind of like a concept in calculus that you learn. You don't have to worry about this yet. All you really need to know right now is if you ever see a fraction, just ignore it, and then the rest of your thing is the slant asymptote. So this slant asymptote is x plus 1. However, if you wanna say for this interesting thing, if you put infinity, if you put as numbers approaching to infinity in all of these, this would approach to 0. And the reason why is the square grows faster than the regular. So x squared grows faster than x. So the bottom will reach infinity before the top. Theoretically, the bottom will reach infinity before the top, which will make the thing 0, because anything divided by infinity is basically infinitesimally small parts, and that's basically 0. So that's why it's not counted, and the x plus 1 is the only thing that's counted in the sine asymptote. And also we're kind of dealing with it going to 0 as well, you know? So that's why it's a slant asymptote. And here's the practice. Here's the slant asymptote practice. So let's do 3x squared plus 6 over x minus 2. So what's the vertical? The vertical is x equals 2. Good, good. So let's draw a graph right here, right? Our vertical is x equals 2, right? Or horizontal, what's our horizontal? We don't have a horizontal. The reason why we don't have a horizontal is because the top degree is bigger than the bottom degree. So the slant asymptote, what's the slant asymptote? We have to do long division. Actually, in this case, we don't have to do long division, but we're just going to do long division anyway. And I'm going to put this 0x as a placeholder, even though we really don't need a 0x. I'm going to put this 0x as a placeholder so it's less confusing. So 3x squared, let's do some long division. So x minus 2, how many times does 3x squared goes into x? It's a 3x time. Because 3x times x is 3x squared. So subtract 3x times x is 3x squared, right? I'm going to put this parentheses so it's less confusing. And then and then subtract, because 3x times negative 2 is 6x. 6x. So subtract 3x squared minus 3x squared is 0. 3x squared plus 0x plus 6x is 6x. 6x plus 6. Okay, how many times does 6x go into x? It's 6 times, so 3x plus 6. 6 times x is minus 6x, and 6 times negative 2 is minus 12. So then we have 18 as our remainder, and then add 18 over x minus 2, and that is our synthetic division. So our slant asymptote is 3x plus 6. Let's erase this. Our slant asymptote is 3x plus 6. So I'm going to draw the slant asymptote. It will probably look something like this. 6 is probably like somewhere like here, so it will probably look something like this. Okay, that'll probably be like the slant asymptote. Okay, the x-intercept is -2. So yeah, it looks something like that. Okay, so 3x. Actually, yeah. Okay, 3x plus squared plus 6, x minus 2. Let's find the x-intercept. The x-intercept is when the top is equal to 0. So x-intercept is 3x squared plus 6 is equal to 0. And subtract 6, divide by 3, x squared is equal to -2. And there's something wrong here because you can't take a square root of a negative. Therefore, there is no zeros. No zeros in this equation. Are there y-intercepts though? Y-intercepts, you put 0 on everything. You put 0 here, you get 6 over -2. Our y-intercept is -3, which is around here. Is there symmetry in this function? Well, there's an even and there's an odd. And if there's an even and an odd degree, there's no symmetry. That's just how it works. So if there's an even and odd degree, it's neither. Therefore, no symmetry. No symmetry. So now we have to plot points, and plotting points is annoying, but it has to be done. So let's do so x and f of x. We're gonna do, so our x and our vertical asymptote is 2. So we're gonna do every value kind of below 2 and every value above 2. So we do 1, 0, -1, -2, and then we do 3, 4, 5, 6. This should get me quite a lot of information about the graph. Maybe not 6, maybe just 5, because and then I'll probably add like -3 as well at the end. So 1, you add 1 in there, you'll get a -9/2. No, wait, yeah, -9/2. No, just -9 if you add 1 in there. But you'll just get -9. 0 will get you, well, we already have the 0. I don't even know what I'm trying to do. -1 will get you -3. So -1 will also get you -3. That's interesting. Wait, 1 gets you -9, so 1, -9, that's like about right here. -1 will get you -3, that's around right here. Okay, -2 is -4. -2 squared is 4 times 3 is, it'll be about -4.5, -18 over 4, right? Yeah, -4.5, so it's around right there, right? And then 3 is 3 squared. 3 squared is 9, 27, 36, 33. So 33, that's a big number. It'll be like all the way up here. Let's just say it's up there. 4 is 4 minus 2, that's 2. 4 squared is 48 plus 6, 54. 54 over 2, 27. That's still a big number. Probably something like that. 5 is 5 minus 2 is 3. 5 squared, 75, 81. 81 over 2, 27. Wait. Yeah, 27. Okay, I still don't know where the graph's going, so I need to plug in more points. And this is probably an inefficient way to do it. There's probably, oh god, okay, this is a terrible line. There's probably better ways to do it. I just don't know, and I just set the whole background yellow. I don't know what happened. I'm not gonna try to fix it because this video is lasting too long. 6 squared is what's 6 squared? 6 squared is 100, 6 squared is 108 or 114 divided by 4 is 114 divided by 4 is 57 over 28.5. So it's going something like this, right? Like the graph's going something like that, right? It's going up, right? And then this section is going something like this. Yeah, and then we don't know what's happening here. So we gotta do -3, -4, and -5. So -3 is 27 plus 6. Will give you 33 over -5, so -33 over 5, which is around, I'd say, right here, right? And then -4, add that in, -6. We have 54 over -6, so -9. That'll be around right here. And then -5, we'll have -5 in, 81, -7, -81 over 7. So it's probably like right here. So the graph probably looks something like this, and it looks really weird, and it actually doesn't really look like a rational graph, but sometimes that's what you have to deal with whenever you're graphing rational equations. That's it, I think. Yeah, that's it for today's episode. Let me see if I actually got the real graph, or if my graph was just absolute bad, if my graph was not representative. So Desmos, and the graph is 3x squared plus 6 over x minus 2. And graphs are weird whenever they don't pass the x-axis. 3x squared plus 6 all over x minus 2. This is the graph. Wait, I gotta take a picture and show it. Okay, right there, that's the graph right there. So it was actually supposed to be like this. So this is supposed to be the graph right here. This is the graph right here, right? That's the graph. Let's erase all of the work that I did. That's the graph right there. So I got pretty close. It wasn't weird. I got pretty close to the correct answer. However, that's gonna be it for today's episode. If you want more slant asymptote help, I'll probably upload another video about slant, horizontal, vertical asymptote, something like that, because this is the most confusing topic there probably is in the whole of integrated math 3, until you get to like sequences, series, matrices, or like conic sections or something. Even those aren't that confusing. This is the most confusing stuff in integrated math 3. So that's gonna be it for today's episode. If you liked it, press like button. And if you want more course suggestions, then suggest them, because I'm running out of ideas. Okay, and just kidding. I'm gonna teach all of this integrated math 3. I might start teaching calculus after that. I'm not gonna teach pre-calculus because the things that I'm doing is pretty much pre-calculus. Because integrated math 3 and pre-calculus and algebra 2, they're kind of intertwined. Except algebra 2 is just a little easier. But I'm gonna teach calculus maybe next, maybe linear algebra or calculus, linear algebra or calculus. So that's gonna be it. So thanks for listening to my update, and see you next time.